Oh, yeah. Let's talk about that one. I think you're right. I mean, modulo arithmetic mistake. Here, I'll write it up. Number 47, well, it's number 32 from section 9.2, which is my number 47. This is your number 47. And it's the sum. And let me show you how to think about this, though. Just, I mean, because your apprehension means that you're not entirely confident on why you did what you did. And you know from previous experience in math classes that doing things you're half sure of often does not lead to pleasant results. Am I right? Yeah. It's more often than not that if you're not sure about a step, especially if it's algebra step, things kind of go bad, don't they? But here, the idea is just this. There's a theorem that says we can rewrite that as the sum. Now, here I'm taking out a logical loan, that the resulting things I'm writing are convergent. This only makes sense if the resulting series I'm splitting are convergent, but these are convergent for precisely the reason that you wrote on your sheet, because they're geometric. So we go, okay, so it's 1 over 1 minus 0.3, 1 over 1 minus 0.8. Yeah. So yeah. Look, there's other ones that are a little bit sneakier than this, though. Also, you can have stuff like let's see here, sum n equals 0 to infinity. How about this? 2 to the n plus 4 to the n over 5 to the n. This problem makes, yeah. Yeah, we got to. Okay. So this is like 2 to the n over 5 to the n plus what? 4 to the n over 5 to the n. I can break up the addition because it's where? In the numerator. In the numerator, right? If that was in the denominator, then we'd be stuck with limit comparison or something. But this we can actually calculate. Then it's pretty much the same step you just made. This is going to be 1 over 1 minus 2/5 plus 1 over 1 minus 4/5, where I'm identifying each piece as being separately geometric. I mean, this step I have skipped that I perhaps should write down at this juncture is that I'm breaking up some of the series and then applying the geometric series results separately to each piece. Yeah. Yep.
Can you like the 9.2 and 40? Like, I understand, like, is there one with the repeating decimal?
9.2, number 4. Oh, the one with the repeating. Is that the 2.55, 0.2155? Sure. All right, let's talk about that. Here, you just got to be careful. Is what this problem is. All right, just got to be careful. So let's write it out. This is 0.2, right? Plus 0.015 repeating. Let me expand on that. What does that mean? This is 0.2 plus 0.015, 15, 15. Okay, you did it. All right. So we understand what's meant. Great. 0.2, this is going to be very boring. This 0.2, it's just going to stick over here and do nothing with everything else, okay? It it stays over here. Now this, we're going to rewrite. This is 0.015 plus 0.123, 12315 plus, and I think at this point it's helpful to start using scientific notation. This is 1.5 times 10 to the what? Yeah, so let's see here. Negative, this one, let's see here. This was, let me write this one. This is 1.5 times 10 to the minus 2. This one right here is 1.5 times 10 to the what? Minus 4. This is, okay, that's a minus 6, right? And so forth. So if you look at it, you're looking at terms like 1.5 times 10 to the minus 4 over, say, 1.5 times 10 to the minus 2. What you got is you got 1 over 100. Every term, and you can see that that's the same, it's the same ratio for every successive term, right? So we got 0.2 plus what? A? What's my A? What's the first term in the geometric series? A is the first term in the geometric series. This right here is my A. So we're trying to look at it as A plus AR squared plus da da da, because we've worked it out that that's 1 over 1 A over 1 minus R. The 0.2 is not part of the geometric series. It's just sitting out there by its lonesome, right? In no way do you multiply 0.2 by something to obtain these other terms. It's separate from that geometric piece. So anyway, we got 0.015 divided by 1 minus 1 over 100. And then you can do the arithmetic, but that's how I think about this problem. This one's a little bit trickier compared to some of the other ones because it's got this extra 2 that's not part of the pattern. That just, yeah. By the way, I got hung up on this one the first day. I don't know what was wrong with me. This one, remember? So how should I look at this? I should look at this as 0.9 plus what? Yeah. So what is my A here? This is A. What's my R? Yeah, R is 1/10. So that gives us the 0.99. We could just do this, right? 0.9 repeated is equal to 0.9 divided by 1 minus 1/10, which of course is 0.9 over 0.9, also known as 1. So this proves that 0.9 repeated is 1. People who say that that's not true are making some kind of distinction between real numbers that are actually equal. And so they're not having a useful conversation with you. The same people will tell you things like 1/2 is not 3/6. 1/2 is 3/6 if we're talking about real numbers. When we talk about real numbers, we agree to work with equivalence classes of fractions, where we consider 1/2 and 3/6 are the same. If you want to say 1/2 and 3/6 are different fractions, and that those fractions are not real numbers, fine. I'm fine with that. They can all be identified with the single real number, which is decimal expansion 0.5, but they have different fraction representations. Be wary of these people. Dr. Sperano. No, I'm sorry. Just kidding. He means well. What I'm trying to say is when somebody says something like that, don't let them make you doubt what you already know about real numbers. That's really my more deep concern for you. You should never doubt that 1/2 is equal to 3/6, you know? Yeah, that was, I'm just messing with you guys. That has to do with, see, the devil's in the details there. The problem there is that, you know, we're trying to use smooth calculus to model something which just is not smooth. That's the error there. Arc length doesn't make sense in that sense. Yeah.
I also had a question about 46, and I want to see if I made the right assumption for 46.
Oh. Number 46 of section 9.2?
Yeah.
We should agree that if tomorrow Darius asks any of the questions that have been asked today, we all will collectively turn to him and bark at him like a dog and not explain why. Would you agree? Will you join me in the solemn pact? Yeah?
Barking like a dog.
You barking like a dog, just woof, woof, just like that. But no one, I forbid any of you to explain it to him. Yes? I think this activity is its own reward. Let's see here. This is section 9.2, number 28. Let's see here. Will there be extra? I suppose I could arrange for some extra credit, but then I feel like you're just going to you're going to just tell Darius to ask something to make sure that the extra credit happens. I'm worried that someone will. Anyway, which one were we on? This one? Is it this one?
Was it 40? Yeah. Yeah, that's the one.
All right. I'm sorry. I'm digressing with nonsense. So your idea is because P series when P equals 2. Now be careful. The P series converges to pi squared over 6, but that doesn't say anything about this one. I mean,
because you have n squared at the bottom.
I like your the big idea you have is I think it's good. This is essentially, I mean, I would say that when n is stupidly big, this is really like 1 over 4n squared, right?
Yeah.
So if we do, I think you're right. If we do a limit comparison, or we could even do direct comparison here too, which I know you're gonna ask me. I know Brian's gonna ask me about. He's gonna ask me about direct comparison. I know this is coming next, and I think you're right. We could do it because this is clearly less than 1 over 2n times 2n, right? Which is 1 over 4n squared. So this, we know that the series 1 over n squared times 1/4 is equal to the series 1 over 4n squared. That's one of the properties of series. For convergent series, you can pull numbers out. Heck, for divergent series, you can also pull numbers out with the proper interpretation. But anyway, that's actually 1/4 pi squared over 6, since we know that by magic. And so actually, if we use direct comparison, we actually get a little bit more. We get that this series converges to something less than pi squared over 24. Direct comparison test indicates that the sum 1 over 2n plus 1 times 2n plus 3, n equals 1 to infinity, is less than pi squared over 24.
So
Yeah.
I can use P series for just a part of this.
We could also use limit comparison to p equals 2. That would work just the same. Limit comparison p equals 2 is another good choice here. Yeah, absolutely. Totally agree. Yep. Telescoping would be, now why would telescoping be better here? Depends on the instructions to the problem. If I say find the sum of the series if possible to get the maximum credit for the, so if I say find the sum of the series if possible, right? And you prove to me it converges by a legitimate method, I'm going to give you a lot of partial credit, right? But to get the maximum credit and perhaps even bonus points on the problem, do what you just said. Identify that this can be rewritten as a telescoping series, and as such, you can calculate its sum. So did you guys know what he's talking about? This we could look at as a over 2n plus 1 plus b over 2n plus 3.
Oh, partial fraction.
Yeah, because it's the product of linear factors, we can rewrite it as a sum of the reciprocals of those factors. Partial fractions. You can work that out, and then one will be positive, one will be negative, and it'll give you a telescoping sum, and you can work out what it converges to, yeah. That's even better than our direct comparison, because it won't give us an estimate. It'll actually show us explicitly what it converges to, which is, pretty nice, yeah. What are the instructions? Which one was this, 9.2? Oh, yeah. So my first two solutions are not legitimate solutions. It says find the sum. We have to do what Josh said because of the instructions. Oh, but unfortunately our time is up. So see you guys tomorrow.
Is there a class after this?
What's that?
Is there a class after this?
Yeah, I do. Yeah, I do. I must go. Yeah, I know. I have to go recover before that class starts. But you guys can ask me questions again tomorrow, right?
Yeah.
When's our math battle? Thursday.
Friday.
Friday the quiz?
The quiz is Tuesday.
And then